Hello, and thank you for attending the presentation of our paper. My name is Andreas Komninos, and I'm an assistant professor at the Computer Engineering and Informatics Department at the University of Patras in Greece. This work was carried out jointly with my students Mr. Konstantinos Tsigkounis and Nikos Politis, and co-supervised by Professor John Garofalakis. In this paper, we present a novel prototype for the monitoring and control of industrial environments in virtual reality, and we're interested here in the presentation and delivery of notifications about events during an industrial process within this context. To begin, let us describe the background of our paper. Industry 4.0 is the upcoming paradigm for manufacturing and industrial system control, based on a network of sensors, devices, machines, and humans. And this network shapes what is termed the industrial Internet of Things. Industrial sub-processes don't need to take place at a single site. In fact, they're flexibly distributed to cooperate in sites across the world. The digital twin concept allows us to unify this distributed industrial process into a single virtual entity in real time, and to monitor the whole thing from a single point. In the past, control and monitoring of industrial processes has traditionally taken place in dedicated control rooms, where engineers and personnel monitor equipment that shows the states of various system components. However, with the industrial process distributed across a range of physical sites and reconfigurable to accommodate diverse sets of production requirements, we must wonder, what will the control environments for Industry 4.0 look like in the future? Let's take an example of a traditional control environment. What you see in the picture here is the control room of the Kozloduy nuclear power plant. This is a kind of really old setup where things are fixed, instruments are fixed, meaning the layout of various controls and displays is permanent, it doesn't change over time. Also, you can note that the environment is quite cluttered, so it can be difficult from the sitting position to see exactly what's being shown in each instrument. And the instruments relevant to particular scenarios are scattered, so the engineer has to continuously shift their attention between them. This can cause high cognitive load, especially during emergencies. Overall, we can say that the display size is large, and in fact, it's a wall-size display, meaning that not all of the relevant instruments can be viewed at any given time, which also contributes to the cognitive load. Engineers have to be physically present in the room in order to do their job, so there is no support for remote access, and finally, the hardware used to implement the control room is dedicated and built for purpose. Moving on, in the next picture you see something a little bit more modern. This is the control room of the International Space Station. And you can see in contrast with the previous example, this is an environment which is completely reconfigurable, meaning that since all the information is digitized and digitally presentable, any engineer can pull up any type of information on their displays and make use of it according to the scenarios at hand. So the information displays can be as simple or as complex as is required, therefore completely adaptable. You can also see that the information displays here are multi-size, so we have things starting from small devices like mobile terminals to single monitor workstations, multi-monitor workstations, and even wall-size displays. And of course, because information is completely digital, we can have remote access, so this information can be accessed from anywhere in the world, and any engineer could theoretically take part, at least, in the orchestration of operations using commodity hardware. Finally, let's look at something a little more futuristic. This screenshot that you see is from a product called Virtual Desktop, which can be purchased and run on commercial virtual reality headsets, and it's meant to replace the standard monitor on a PC. So what you can do is you can open up programs like you do on any PC, and you can run them in Windows, which are then arranged in a virtual environment around yourself as the immersed user. An environment like this is infinitely reconfigurable because it's not constrained by the screen real estate, like for example the multi-monitor setup in the ISS control room. It's also infinitely adaptable because you can arrange these windows and this information anywhere around you, above you, beneath you, just 360 degrees around the user. Okay. And one big advantage also is that you don't need an actual room to do this. The room is virtual, so all you need is a physical chair and maybe a physical desk. But the information display area is pretty much the whole virtual world. Another advantage over the digitized control room environment is that this type of environment supports mobile access. So you can remote log in from another PC with an appropriate VR headset, of course, or you can remote log in with a mobile device like a smartphone attached to a VR headset, and you can participate in this type of environment from anywhere. And of course, all you need is a VR-enabled rig. So to set our work in a realistic context, we chose marine environments as a use case example. If you think about large commercial vessels like cargo ships, they're essentially floating industrial installations, and they have distributed components and manpower to manage electricity, power generation, mechanical equipment, and navigational equipment. To achieve various operations such as docking, loading, and so forth, the subsystems must be coordinated to work together, which is the job of the captain and of the officers of the bridge. So indeed, if you look at the modern ship's bridge, the analogy with the evolution of control rooms shown before becomes quite apparent. Even more, the remote management of ships is very important today and will be even more important in the near future. For example, the collection of onboard data and remote execution of analytics for cases like preventive maintenance is very important, since it can help operations management from the ship's base to give instructions to the crew to proceed with repairs before they happen unexpectedly or at an inconvenient place and time. In the future, we will begin to see unmanned operations of cargo vessels, since the requirement for large human crews is a limiting factor to performance and cost, and of course, there are cases where unmanned operations might be preferable due to adverse prevailing conditions, like weather, piracy in international waters, journey lengths, or dangerous payloads, and so forth. Therefore, to be able to bring the complex control environment of a big ship to a remotely positioned engineer is a realistic and interesting prospective use case. To investigate our problem domain, we designed and implemented a system which is able to collect, process, and manage data from a range of IoT sensors using the open source ThingWorks platform as the central repository. Sensors are defined in the platform according to their function, maximum and minimum values, and the range of normal values that they should have, and the type of instrument that should be used to display the value. For example, a gauge or a digital readout, and so forth. The incoming data can be processed and filtered in real time and then passed on to an Apache Kafka data stream, which means they can be consumed by external services. So from this data stream, we created a visualization system which can dynamically produce a range of control room displays, for example, a large video wall dashboard or a multi-display dashboard for a single workstation, or, as related to our paper, a virtual reality environment which the user can immerse themselves. We'll focus a little bit more on the VR environment since this is the subject of our current paper. The environment here is shown as an octagonal room, with each wall dedicated to a group of instruments related to some function of the ship's operation. So for example, we have a wall for the navigational instruments, one for the engines, and so forth. Apart from the instruments, our system can also display video streams, and for our experiments, we dedicated one wall for this function. The user's field of view is shown in this slide here as a blue shaded area. And the setup is so that the user can see an entire wall when looking directly at its center, and almost half of each adjacent wall. So if we suppose that at any point in time an instrument begins to raise an event, then a notification is shown to the user to alert them to that event. And of course the instrument can be anywhere around the user, so we therefore say that the angle between the user's field of view center point and the event raising instrument is angle theta, as you can see here in the slide. And we'll use this angle definition later on. Next, here's how we design notifications. So first of all, we have a stack of notifications that appears to be on the user's right-hand side. The notifications are semantically queued, so color denotes priority based how far off the normal range the value reads. So green is normal range, orange is somewhat off normal, and red is way out of normal. And a textual description in the notification panel here shows the wall name and the instrument name so that the user can find this instrument easily. The stack also puts new notifications at the top, so all notifications are stuck at the bottom, whereas the new ones just appear at the top here. And in terms of a spatial queue, we present a three-dimensional arrow, which you can see here on the top of these screenshots, and that points in the direction of an instrument, both horizontally and vertically. And that gives, of course, the user some ability to quickly locate the instrument related to the event. Now we should also say that in order to dismiss a notification in our prototype system, all the user has to do is basically place this white dot that you can see here. This is the center of the field of view on the instrument that raised the notification. Keep it there for 5 seconds. So for our experiment, we had three main hypotheses. The first one was that the addition of a spatial queue can have an effect on the participant's response time to notifications in the VR control room environment. Our second hypothesis was that the response time to notifications can be affected by the angle between the participant's viewpoint and the event-raising instrument. So the further away it is in terms of radial distance, the longer it might take. And our third hypothesis was that the response time to important notifications can be affected by semantic cues for notification priority, and that's mostly a call coding. In our experiment, we investigated two conditions. The first one was using a semantic cue only. The second condition was using a combination of spatial and semantic cues. Our experiment design was repeated measures. It was counterbalanced to prevent bias in the results. And we had 5 sessions in each condition with approximately 10 events per session, and also with a time limit of about 3 minutes per session. The participants that we recruited were 17 in total. They were between 25 and 38 years old. Most of them had no previous VR experience, and what we asked them to do is watch the video stream which was displayed in the main wall of our virtual room, and also to respond to notifications as quickly as possible, trying to dismiss higher priority notifications before they did the lower ones. The data that we collected was notification issue and dismissal time, the angle to issue notifications, the number of ongoing notifications on issue and on dismissal, and in total we collected data for 646 notifications in the SC condition and 558 notifications in the MC condition. This difference owed basically to the random timing of the notifications, which meant that one condition had slightly fewer. In terms of our findings, at first glance, we saw that the MC condition resulted in almost 20% shorter dismissal time across all sessions, but this difference was not statistically significant. We noted, though, that there existed a substantial learning curve across all these sessions, and therefore we repeated the comparison, discarding the first 2 sessions, assuming that the participants were still familiarizing themselves with the system during these 2. This is despite the fact that we gave them plenty of time to familiarize themselves with the system in the beginning of the experiment. Now, when comparing the data from these sessions 3 to 5 only, we note again that the same reduction exists, about 20% in response time, but this time the difference is indeed statistically significant. Further analysis showed that the priority level of notifications did not seem to have an effect in the SC condition, but we found a statistically significant difference in the dismissal time between low and high and medium and high priorities in the MC condition. So taken together with the previous findings, it seems that the presence of spatial cues results in lower response times, and it seems to help with the response time to high priority notifications. Finally, we didn't find any statistically significant effects of the absolute angle between the user's field of view and the event-raising instruments on the response time. So overall, we can state that we found evidence to support our first hypothesis, that spatial cues can indeed improve response time to notifications. Further, it seems that spatial cues help users respond more quickly to high priority notifications, which is of course rather important and provides partial support for our third hypothesis. We weren't able to find support for our second hypothesis relating to angles, but in a sense, we think this is quite good news, since it means that the physical motion, i.e. the body rotation required to find the relevant information, plays an insignificant factor at the information-seeking ability of users. We think our system presents a promising idea for which we have only taken preliminary steps to investigate. Our work has some limitations, for example, the fact that users didn't really interact with the control environment, for example, pressing buttons or manipulating other controls, which is a process that might affect attentional blindness to new notifications. So we need to look into that a bit further at a later stage. We also definitely need to target more representative user populations, and we would also like in the future to investigate other spatial and semantic cues, such as, for example, using different sound types to alert to notification priority, or using 3-dimensional audio to provide spatial awareness for event-raising instruments. Thank you for your attention, and if you would like to see what our prototype looks like, we have a video on YouTube and you can download and run our demo application for Android devices. The links are here and in the slides, and you can also find them in the paper. If you're interested in the source code for this demo, please write to us and we'll be happy to consider the request. Thanks again.